Okay, let us continue the part 2 of the course. Okay, so PI is defined as the expectation of, okay, let me input this first. Okay, tilde. Let me see where is the tilde. Oh, okay, here. S. Okay, SI. Oh, sorry. I. Okay. And a square. Okay, because PI is defined as the expectation of the square of the absolute value of S tilde I, where S tilde I is the I symbol to be transmitted. So it is equal to greater than or equal to 0. Okay, of course, because power is always greater than or equal to 0. Okay, so in order to prevent PI being smaller than 0, okay, we must define the following equation, function. Okay, so x plus, okay, is defined as, okay, defined as this. Okay, defined as okay, let me see how to input cases. Okay, oh, good. Okay, so let me input first. Okay. Okay, so let us define this function. X plus is defined as x when x is greater than or equal to 0. And x plus is defined as 0 when x is smaller than 0. Okay, then excuse me. Okay. Okay, like this. Okay, so PIOPT is equal to minus beta times natural log 2. Oh, sorry, 1 over beta natural log 2 minus 1 over rho lambda I plus, where I is equal to 1 to R. Okay, where small w. Okay, where PIOPT is the optimal solution to to PI. Okay, define mu is defined as minus one over parenthesis rho beta natural log 2. Like this. Define mu as minus 1 over beta natural log 2. Then PIOPT is equal to mu minus 1 over rho lambda I plus, where I is equal to 1 to R. So this is equation 5. So this completes the solution. Let me insert a black square and align right. Do you have any problem? So let me save. This is chapter 3, page 72, problem 1. And save to Blackboard of Mimo. Good. Let us go back to the slides. And next, this point, I think it is not correct. On the textbook. So I changed the color of this point to gray. And mu does not have a closed form expression. What is a closed form expression? Let us see the handout. Closed form expression. Page 73, problem 1. What is a closed form expression? Solution. In mathematics, a closed form expression is a mathematical expression that can be evaluated in a finite number of operations. It may contain constants, variables, certain well-known operations. For example, addition, subtraction, multiplication, and division. And functions, for example, nth root, exponent, logarithm, trigonometric functions, and inverse hyperbolic functions. What is inverse hyperbolic functions? It is not the key point here, but usually no limit. The set of operations and functions admitted in a closed form. Let me close it. Expression may vary with author and context. For example, the expression f of x is equal to summation I is equal to 0 to infinity x over 2 to the power of I is not in closed form because the summation entails an infinite number of elementary operations. Okay. However, by summing a geometric series, this expression can be expressed in the closed form. F of x is equal to 2x. Okay. Let us go back to the slides. Okay, next page. Okay, let me change the pointer. Okay, the steps in the water filling algorithm are defined in table 3.1. Okay, let us see table 3.1. Okay. Table 3.1 is the water filling algorithm for eigenbeamforming. Okay, first, set the iteration count p to 1 and compute mu by solving the following equation. Okay, mu is equal to 1 over r minus p plus 1 times 1 plus 1 over rho times summation I is equal to 1 to r minus p plus 1 over lambda I. Okay. 2. Using the value of mu obtained above, solve the power pi opt for the ith eigenchannel using the following equation. Okay, next page. PIOPT is equal to mu minus 1 over rho lambda I, where I is equal to 1 to r minus p plus 1. Okay. 3. If the power is allocated to the channel with the lowest gain, that is, if PR minus p plus 1 OPT is smaller than 0, discard that channel by setting PR minus p plus 1 OPT be equal to 0 and return the algorithm with the iteration count p incremented by 1. Okay, next page. 4. Repeat steps 1, 2, 3 until all channels have been allocated power. Okay, let us go back to page 74. Okay, table 3.1 using the expressions for PIOPT and mu to iteratively compute the set of values for Pi that maximize CEIG. Okay. The resulting set PIOPT are then substituted into equation 3.27. Okay, let us go to equation 3.27. Okay. Okay, in equation 3.27, we can see that CEIG, that is, the capacity with eigenbeamforming, is given by summation I is equal to 1 to r, where r is the channel rank, log 2 of 1 plus rho, where rho is the SNR at the receiver, times expectation of the square of the absolute value of S tilde I, where S tilde I is the ith symbol to be transmitted, times lambda I, where lambda I is the ith largest eigenvalue of the matrix H times H Hermitian. Okay, let us go back to the slides. Okay, let me see to the slide. Okay, here equation 3.27 to obtain the optimal capacity COPT. Okay, thus COPT is equal to summation I is equal to 1 to R log 2 of 1 plus rho times PIOPT times lambda I. Okay, so next let us go to section 3.5.2. Discussion of the water filling algorithm. Now that we have defined the water filling algorithm, we will attempt to understand it in a more intuitive way. Figure 3.3. Okay, let us see figure 3.3. Okay, figure 3.3 shows the depiction of the water filling algorithm where R is assumed to equal 5. So you can see that there are 5 eigenchannels. Okay, so this is for the case P is equal to 1, and this line denotes the value of mu. Okay, and here are 1 over rho lambda 1 to 1 over rho lambda 5, and here are P1 OPT to P3 OPT. Okay, so figure 3.3 illustrates the algorithm for the case where R is equal to 5. Okay, that is, the channel rank is equal to 5. Part A depicts, part A is this figure, depicts the values of 1 over rho times lambda 1, where I is equal to 1 to 5, and mu after performing steps 1 and 2 of the algorithm when P is equal to 1. Okay, let us go to the algorithm to see steps 1 and 2. Okay, the step 1 of the algorithm is to set the iteration count P to 1 and compute mu by solving the following equation. Okay, mu is equal to 1 over R minus P plus 1. Okay, now it is equal to 5 minus 1 plus 1. Okay, so it is equal to 5. And times 1 plus 1 over rho, which is the SNR at the receiver. And the summation I is equal to 1 to 5 and 1 over lambda I. Okay, this is the step 1. Okay, step 2, using the value of mu obtained above. Okay, solve the power PIOPT for the ith eigenchannel using the following equation. Okay, PIOPT is equal to mu minus 1 over rho lambda I, where I is equal to 1 to 5. Okay, let us go back to this slide. Okay, as is evident in this figure, the eigenvalues are assumed to be sorted from largest to smallest, which is a key assumption that underlies the water filling algorithm in table 3.1. So in this figure, lambda 1 is greater than lambda 2, is greater than lambda 3, is greater than lambda 4, is greater than lambda 5. Okay, because of this fact, the quantities 1 over rho lambda I become larger as the index increases. Okay, we can see that 1 over rho lambda I becomes larger and larger when the index increases. Okay, 1, 2, 3, 4, 5 increase. Okay, which means the symbol power levels decrease with index, since PIOPT is equal to mu minus 1 over rho lambda I. Okay, so you can see that P1 OPT is greater than P2 OPT is greater than P3 OPT. Okay, and for eigenchannels 4 and 5, because mu is smaller than 1 over rho lambda I, so the PIOPT is smaller than 0, and we set PIOPT to 0. Okay. In this example, 1 over rho lambda I is equal to 4 and 5 are greater than mu. So PR minus P plus 1 OPT is equal to P5 OPT. Okay, because R is equal to 5 and P is equal to 1. Okay, it's smaller than 0. Excuse me. Therefore, according to the algorithm, the power associated with eigenchannel 5 should be set to 0 and P incremented to 2. Okay, next, part B. Okay, let us go to part B. Okay, in part B, okay, let me change the pointer. Okay, P is equal to 2, and this is the value of mu, and we have discarded eigenchannel 5. Okay, so this can be discarded, and we have 4 channels now. Okay, part B depicts the situation after repeating steps 1 and 2 when P is equal to 2. Okay, after incrementing P, the denominator in the coefficient of the expression for mu in step 1 increases. Okay, let us go back to step 1. Okay, after we increase P, okay, from 1 to 2, okay, this term R minus P plus 1, okay, will be changed from 5 to 4. Okay, because 5 minus 2 plus 1 is equal to 4. So this coefficient is changed from 1/5 to 1/4. Okay. So let us go back to the slide. Okay, so the denominator in the coefficient of the expression for mu in step 1 increases, okay, from 1/5 to 1/4. But since the number of terms in the summation decreases by 1, okay, what is this mean? What does this mean? Okay, let us go to step 1 again. Okay. Okay, in this summation, the number of terms, okay, in part A is equal to 5. And in part B, R minus P plus 1 is equal to 5 minus 2 plus 1. And it is equal to 4. So number of the terms in the summation changed from 5 to 4 terms. Okay, let us go back to the slide. Okay, the quantity in brackets is smaller. Okay, what does this mean? Let us go back to step 1 again. Okay, so the value inside the brackets becomes smaller. Okay. Okay, it is 25 minutes. Let us take a break.